right, good afternoon, everybody. How's everyone doing? Good, I hope. Okay, so today we're going to continue along with our discussion of what can we do in order to even further improve our performance. And we're going to do that today by thinking about, well, beyond pipelining, what can we do to even further improve our performance? And what we're going to consider is doing parallel execution. So if we're doing things, if we're not doing things in parallel, then the best we can do in terms of our CPI, or cycles per instruction, is 1. Once we start doing some things in parallel, then we can actually try to get that CPI to be even lower than 1. And so that's what we're going to look into today, and as well as what are the complications that come about when you start to do things in parallel. So, to get started, let's first define what we mean when we say thread-level parallelism. So basically, we're going to take a large computation, and we're going to divide it up into multiple sections or multiple threads, and we're going to execute these different threads in parallel. Now, these different threads can be either related to each other or not, and so the two alternatives to consider is one where the multiple threads are independent of each other, but they do contend for shared resources like your memory or your shared I/O devices, things like that. Another choice is to actually have threads that communicate with each other. So the minute you have threads that you communicate with each other, then you actually have to make sure that things are happening at the right time, so that the things that they're communicating with each other are being sent and received at the right time. And that's what we're really going to focus on today. So if you need a communication model, there's two communication models that we consider. The first is a shared memory model. So what do we mean here? Well, basically, if you take a look over here, we've got 3 threads executing in parallel, but they all share the same memory. So that also means that they all share the same address space. And so the way that these parallel threads would communicate with each other is by simply doing loads and stores into this shared memory. Okay, so one thread could store a value into location 0x100, the other one would then read the value, and in that way they communicate with each other. An alternative to shared memory is what's called message passing communication. So how does this work? Well, this looks like this picture over here, where now each one of these threads is essentially you can kind of think of it as it's got its own memory, or it's got its own address space. Okay, so there isn't this notion of a shared address space anymore. And so now, in order for these threads to communicate with each other, they actually have to send explicit messages from one to the other across this shared network. Okay? And so those are the ways in which these multiple threads can communicate with each other. And we're going to focus on shared memory today. Okay, so, well, what's the problem that happens the minute we start to do some of these things in parallel is that we have to start worrying about synchronization between these threads. And so there's multiple reasons that can lead to needing to synchronize between your threads. So here is an example of the first one. Suppose that you have some piece of code and it's just running, in one thread, and then you've got some big computation that you want to divide up into multiple threads so that they can execute in parallel. And so here we show, 2 threads executing in parallel. But then before you continue with the rest of your program, you have to wait and make sure that all those threads completed their computation. And so we have this join step down here, which is basically ensuring that all the threads completed their execution up to a certain point before we can continue with the next step. Okay, and so this requires some form of synchronization amongst those threads. Another situation is what we call producer-consumer. So here what we have is we have one thread that's producing some value, which the consumer is depending on. And so the consumer can't begin execution until after the producer produced what it needs to produce. Okay, so once again, we're going to have some kind of precedence constraint. In this case, it'll be the fact that the producer has to come complete before the consumer can run. And then yet another situation that requires synchronization is what we call mutual exclusion. And so we have resources that, that are shared amongst our processes or amongst our threads. And we need to make sure that at any point in time, we only assign as many threads to these resources as we have available resources. And so the operating system that we've learned about is responsible for making sure of that. But more importantly, the question is, how does it do it? And so it's going to make sure that at any point in time, it only assigns, it only allows as many processes as it has resources to actually run at the same time. And we're going to take a look at a mechanism for doing that today. Okay, so last kind of high-level thing before we get into the nitty-gritty details. So we want to define what does it mean for a multi-threaded program to be a thread-safe program. So the way that we define this is, imagine that you have a single processor that these multiple threads need to run on. We already know how to use our operating system in order to switch between multiple processes that share a single CPU. So in the same way, we can also do the same thing with the threads, where the operating system would switch between these threads in a time-sharing manner. And so each one would get to run for a little while, then the next one would get to run, and so on. So the behavior that you would expect to get in such a machine is what we think of as running a multi-threaded program on a single processor. Okay, so you know exactly that only one instruction will actually be executing at a single time, and so whatever that processor, single processor, would produce is what we would expect for it to produce, even if you give it multiple processors. So it's said to be thread safe when it's running on multiple processors if what it produces is the same as what it would have produced when it was running on a single time-shared processor. Okay, so for the rest of today's lecture, though, we're not going to worry about needing to do this time sharing. We're just going to assume that for every thread or every process we have, it's got, each thread has its own processor, and so that these things can be running in parallel. And the focus of today's lecture is going to be, how do we do this synchronization between these different processes? Okay, so any questions before we continue? Good. All right, so what do I mean when I talk about synchronous communication? So let's start off with this simple example. We've got here a producer thread and a consumer thread. And what's going on is this endless loop in both cases, where my producer is running some instructions, XXX, which make it update some value, which it produces some character, which it then sends over to the consumer, and then it goes back to loop and repeats the same thing. The consumer, on the other hand, is waiting to receive some character. With it, it then runs some instructions Y, and then it repeats its own loop. Okay? So as from an execution standpoint, it looks like you're basically running, XXX for the first time, and then you're sending your first character, then you're running XXX for the second character, then you're sending it, and so on. And on the receiving end, it looks kind of similar, where you're receiving the first character, you're doing something with it, which are these Y1 instructions, then you receive the second character, you do Y2, and so on. Okay? So, if we look at these two processes, is there any kind of relationship between them? Is there any kind of synchronization that we need to make sure happens if we want these two processes to communicate with each other? Can anybody think of what we might want to make sure is true? Well, what would it mean for my consumer to receive a character if my producer hasn't sent one yet? We wouldn't know what that means, right? And so we want to be able to define what we call precedence constraints, okay? And this is how we, this is our notation for precedence constraint. It's kind of this little rounded less than or equal to sign. And so this is basically saying that A must precede B. Okay? So what kind of precedence constraints do we have in this example? What must precede what? Yep.
The send has to be before the receive.
The send has to be before the receive. Exactly. Okay, so I need to have a way of expressing that send of I must happen before receive of I. Are there any other precedence constraints that I need to be concerned about here? Can anyone think of any? So take a look at the definition of my producer, okay? My producer has this character C that it's going to put the data that it wants to transmit over to the consumer in. So imagine if I, ran through XXX1 and send and then XXX2 and send before my receive one ever happened. Well, what that would imply is that my producer produced two things, and the second value overwrote the first value, and now the receiver has no way of getting that first value. Okay? So in addition to making sure that my send of I happens before my receive of I also need to make sure that my receive of I happens before my send of I plus 1. Okay? Everybody okay with that? Good. So, we need to figure out a way of making sure that these constraints are actually satisfied. Now, if we have, two programs that are, so tightly synced with each other, it might be, kind of hard to actually get any parallelism out of them. And so generally what we want is to be able to define some precedence constraints, but have a little more wiggle room than, defining an exact ordering. And so the way we do that is basically by using what we call FIFO, or first in, first out buffers. So what does this mean? Instead of having a single character, a single variable that is a character that to hold the value that I'm trying to transmit from the producer to consumer, instead I have a buffer that can hold n such values. Okay, and so what does this do? This allows the producer to get up to n values ahead of the consumer. Okay? And so it relaxes the precedence constraint a little bit so that instead of receive of I needing to happen before send of I plus 1, it just needs to happen before send of I plus n. Okay? So let's take a look at how we might implement this first in, first out buffer. So typically, it's implemented as what we call a ring buffer. It's called ring because you basically rotate back from the end of the buffer to the beginning and keep using it over and over again. So let's take a look at an example here. So imagine that we have a 3-element buffer, and it starts off empty. And the first thing that I have to do is to actually send a character, right? So here we go, we send character 1, and so I put that as my first character in my buffer, and notice that my pointer on my writing side has now shifted over to point to the next location, which is free and available for me to write a new character to. Okay? So now, before I actually do a receive of character 1, it's perfectly fine for me to do another send. Okay, so here I did another send. Sorry, the first one was C0. The second one is C1. So perfectly fine. My buffer is not full, and I have. So now at this point, I could either, receive or send. So let's see what happens in this example. We happen to do another send. Okay. So now my buffer is full. So can I do another send at this point? No, I must do a receive before another send could possibly happen. Okay, and so what's going on? So I've got a full buffer, I've got a write buffer that's pointing at a non-empty location, and so it can't send anything new. So now I start to receive the characters on the receiving end. And so the first thing it's going to do is it's going to receive the first character, which was C0, and the read pointer will move over to the next location of the next character that it needs to read, and so on. Okay, so I can read another character, I can send another character, and as long as my buffer is not full, I can send characters. As long as my buffer is not empty, I can receive characters. Okay? Any questions about that? Good. All right, so now let's see if we can try to actually implement this, this FIFO buffer using shared memory. Okay, so imagine that we have a piece of shared memory which defines this buffer. So both the producer and the consumer have access to this region of memory, which is an n-element buffer. And they also have access to these pointers in and out, which tell us where to write into the buffer and where to read out from the buffer. Okay? And so here's our first attempt at trying to, define how these producer and consumer can implement their send and receive routines. And so what we're going to do is when the producer has a character to send, it's going to take the character that it has to send, put it into the buffer at the location pointed to by the pointer in, and then it's going to increment in to point to the next location. And of course we have this mod n because it's a circular buffer. Okay? So we just wrap around. Any questions about that? Good. And so what about our consumer? Consumer is going to do something similar. It's going to read from the buffer, except that it's going to read the location that's pointed to by the out pointer rather than the in pointer. And whenever it reads a value, then it's going to take this out pointer and increment it by 1, again mod n, so that you rotate around to the beginning. Okay? So what do we think? So we've got some shared memory. We have a way for these two processes to communicate information with each other. Does this code work? What do we think? Yes, no, shout out your answers. No, good. Why doesn't it work? Because I haven't actually taken care of any of the precedence constraints, right? There's nothing that's preventing this piece of code from, say, trying to, have the consumer receive a character before the producer ever produced one, right? So we need to have a mechanism of specifying these precedence constraints in our code. So how do we do that? Well, in order to do that, we need to have a new data type, which is called a semaphore. And this was first introduced back in 1962. And the way semaphores work is as follows. So when you declare a semaphore, you set it equal to some integer that's greater than or equal to 0. Okay, so in this example, we're setting our semaphore s equal to k. So we're initializing it to the value k. And then there's two types of operations that can be performed on semaphores. The first is a wait operation. So when you wait for a semaphore, what that means is it's not going to allow you to proceed to your next instruction until it is the case that your semaphore has a value that's greater than 0. Once your semaphore has a value that's greater than 0, then it's going to decrement that value of that semaphore by 1, and it's going to allow the instruction after the wait to go ahead and proceed. Okay? Similarly, we're going to have a signal instruction. So what is a signal instruction going to do? It's basically just going to take the value of my semaphore and increment it by 1. Okay? So you can imagine that if I have a semaphore that's initialized to 0, then anybody who's waiting for it initially can't run. But then if there's some process that comes about and signals it, then one of these waiting processes will get to run. Okay? And so let's take a look at that in more detail. So basically, what these semaphores allow us to do is essentially to describe this constraint that we've got here, which is that signaling of S of I must precede the weight of S of I plus K. Or another way to say that is the call to the signal of S must complete before the ith call to signal must complete before the I plus kth call to wait. Okay? And so we're going to make use of these semaphores in order to try to add some of these precedence constraints requirements to our code. So let's take a look at the kinds of things we can do with semaphores. So imagine that I have two parallel threads here, A and B, and A has, instructions A1 through A5, and B has instructions B1 through B5, and what the constraint that I want to satisfy here is that instruction A2 should execute before instruction B4. Okay? So how do I do this? Well, we follow basically a very simple recipe. The recipe is as follows. I'm going to define a semaphore and initialize it to 0. And then, once I've executed the instruction that's at the beginning of the arrow, I'm going to signal my semaphore, so that will increase the value by 1. And then, at the end of my arrow, I'm going to have a wait for my semaphore, which is going to make sure that this before instruction is not executed before this signal happened. Okay? And so by adding these signal and wait instructions, I'm able to ensure that the precedent constraint is actually satisfied, where there is no way to execute both of these threads in a way where A2 would not precede B4. Does everybody see that? Any questions? Good. Okay, so this is how we use semaphores for precedence constraints. We can also use semaphores for resource allocation. So imagine a scenario where you have K resources, and you need to make sure that you're never allocating more than K of those resources. So what you would do in this situation is, instead of initializing your semaphore to 0, you would initialize it to K, equaling the number of resources that you have available. And then, before you make use of one of these shared resources, you would have a wait semaphore instruction, which would make sure that the code following it would not run unless one of the resources was available for you specifically. Okay? So if you got past the wait S instruction, then that would mean that one of the resources was allocated to you, and the value of the semaphore would get decremented by 1, so that the new value of the semaphore represents how many resources you have left. Okay? So in this way, then what's going to happen is that all these different processes can basically have a piece of code that's wrapped in this wait followed by a signal. And so that will ensure that only up to K such processes or such pieces of code will get to run. Okay? So again, in order to deal with resource allocation, for the shared resource you would have a wait S before the piece of code that uses the shared resource, and a signal S once you're done, in order to return the shared resource back to the pool so that somebody else can go ahead and use it. All right, so now let's go back to our code of trying to implement this n character buffer in shared memory, and see if we can do a little bit better than we did before. Okay, so one of the things that we said we definitely need to make sure is that our producer produces a character before our consumer tries to consume something, right? So we're going to use semaphores in order to try to do that. So let's take a look at how. Well, what do I have here? I've got a semaphore, let's call it characters, which it's going to represent, how many characters are in my buffer. And initially, that number is 0. Okay, so initially I have no characters in my buffer. And the way this code is going to be modified is I'm going to have a signal characters call at the end of my producer code, and await characters call at the beginning of my consumer call. Okay, so what happens? Initially, my semaphore is equal to 0. And so that means that this wait characters is just going to sit there and stall. It'll basically just keep waiting until it is the case that the character semaphore becomes a value greater than 0. Okay? So when does that happen? That happens after the producer has actually put something into the buffer. Okay? And so in this way, we ensure that the producer puts something into the buffer before the consumer tries to make use of it. And so the constraint that we're satisfying here is that send of I precedes receive of I. Okay? And also the number of characters in the buffer is represented by this character's semaphore. Okay? So, are we done? Have we satisfied all of the constraints that we need to satisfy? No, right? All we've made sure so far is that the producer goes before the consumer. But we haven't made sure that the producer doesn't overwrite things that haven't yet been consumed, right? So we need to make sure that at any point in time, there's only up to n values still waiting to be consumed. So how do we do that? Well, we add yet another semaphore. Okay? So this semaphore we're going to call spaces because it's going to represent how much space is left in my buffer. Okay, so how many new characters can my producer add to this buffer? And so for this semaphore, it's going to be initialized to n because initially I have n locations available in my buffer. All right? So how do I make use of this semaphore? Well, now, at the beginning of my producer, I'm first going to wait for spaces. So what is that going to ensure? That's going to ensure that if my producer runs several times and has actually put n things into the buffer and the consumer has not yet run at all, that the producer is now going to stall on its next wait spaces call. Okay? And so it can't run if spaces is not, greater than 0. And then on the consumer side, at the end of its code, once it's done processing a character, then it's basically making a space available in the buffer again. And so it's going to signal spaces to indicate that it just made a new space available in the buffer. And so even if it was full before the consumer ran, there's now one space that the producer can put a new character into. Okay? Any questions about that? All right, so this solution does actually work as long as we only have a single producer and a single consumer. And we're going to get to, what do we need to do to also handle multiple producers and consumers in a little bit. But before we do that, let's take a look at, some other types of problems that can arise that we want to deal with. So, suppose that I have, two users of a bank account, and they're using, different ATMs, but they're trying to access the same account. Let's call this account the 6004 account. And each one of these users is trying to take out $50. Okay? So I have some piece of code which is going to basically take care of debiting the account by $50 when the user takes out $50. And so what's going on here? It's basically reading the balance of the account, then it's decrementing it by the amount that the person's taking out, and that goes back into the balance account variable. Okay? Looks pretty simple. So, what's supposed to happen? Well, imagine that, each person is represented by one thread. And so we have, one person would come in, and if you can assume that T0 has the address of this balance account variable that we're trying to read and write to, you would load the contents of what's at address T0 into T1. So that means you're loading the balance. And then you're subtracting the amount that you're taking out of it, which is in A1, since A1 is the second argument. And finally, you take the updated T1 and you store it back into the same location that's used to store the account balance. Okay? And so basically what would happen is, assume you had $1,000 in your account and you came to take 50 out, you would end up with $950 at the end of this. And now thread 2 would come along and it would read the value of the account, and now it sees that there's $950 in the account. It takes 50 out and it ends up with $900. And, you know, everything looks good. We took out a total of $100, and my account balance went down by $100. Okay? But obviously, it's not as simple as that, right? Imagine that instead of executing the way I just showed you, the instructions were interleaved. Okay? So they look something like this. So now let's think about what happens in this situation. So in this situation, I started off with the same $1,000, and my first guy comes along and reads the balance, and that says, okay, it sets T1 to 1,000, okay? But then I switch over to thread 2, and thread 2 comes along, and it reads the value of my account balance, and it also reads 1,000. Right? So now it's going to subtract 50 from 1,000, it's going to get 950, and it's going to store that back into the account balance. Then I'm going to come back to thread 1, which is also going to subtract 50, but it's subtracting 50 from its version of T1. Remember, each process has its own copy of the registers. Okay, so it's subtracting 50 from 1,000, not from 950, even though thread 2 has already taken $50 out. And so what ends up happening is that the value that gets stored here at the end of executing both of these threads is 950. Okay, so what did I do? I took out $100 from the account, but I only decremented the account value by 50. We would all be very happy if our bank accounts worked this way, but certainly the banks would not. Okay, so we need to have a mechanism to make sure that this doesn't happen. And so what we're indicating here is that sometimes you have a sequence of instructions that have to all happen together. We call this basically a critical section, okay? So if I start executing this load, I must follow it with a sub and the store before another thread can call that same piece of code, okay? And so in order to do that, I have to basically add a new constraint, which we call a mutual exclusion constraint. So either process thread 1, can be accessing this critical region, or thread 2 can be accessing this critical region. I don't care which one accesses it first, but they can't both access it at the same time. Okay, and so basically another way of thinking of this is that we need to have some kind of wrapper around these instructions to make sure that the instructions are essentially executed atomically. What do I mean by that? I mean that the load, the subtract, and the store are all executed as if they were a single instruction. So nothing can intervene in the middle of them. Okay? So let's see, how we can do that with our semaphores. So here's my code for checking the value of my balance and then decrementing it and storing a new value. Right? So together, these form a critical region. So what I'm going to do is I'm going to want to specify a mutual exclusion constraint, which basically says, this is what the representation of mutual exclusion is. This basically says that either A precedes B or B precedes A, but they can't both run at the same time. Okay? So how do I do that? The way that I do that is, again, with the use of a semaphore, but a slightly different use. Here what I do is I define, let's say, a lock, which basically locks this critical region, and I initialize that lock to 1. Okay, so by initializing it to 1, if I then wait for the lock at the top of this critical region, then only one of my 2 threads is going to be able to access this piece of code, either thread 1 or thread 2, but not both. Okay, and then at the end, once I've done accessing the balance and updating it, then I go ahead and I signal the lock so that the other thread can go ahead and deal with the balance. Okay, any questions about that, first of all? Yes? Mm-hmm.
It won't run and that slot is wasteful?
It would be wasteful if it was the case that the first process had started and it also ran the wait and actually got a hold of that semaphore. But if you're in a situation where your process 2 happens to be running first, then it's going to be the one that grabs that semaphore, right? And so because it was its turn to run next, it basically got priority and got to run it first. And so yes, it's wasteful in the sense that you're not going to be able to do these 2 things in parallel, but at least it's going to lead to correct execution, right? We have to make sure that when there's a critical section, only one of them gets to actually execute at any point in time. Okay? So we can only allow parallelism when it's actually safe to do it. Okay? And that's what these semaphores are making sure of. Any other questions? All right. So this leads to another question, which is, what should be the granularity of this lock, right? I could go as far as, saying I have a single lock that locks all the accounts, in the bank. That would be very simple to implement because you'd only have to have one lock, but you can imagine that you want to be able to access multiple different accounts at the same time and be able to take cash out of multiple ones, right? So that's probably a little too constrained. On the other hand, if I go to the other extreme and I make a lock for every single account, that's going to become a huge number of locks and semaphores to manage. And so that's going to lead to performance problems as well. And so more often than not, what's actually happens is something in the middle. Right? So you might have a scheme that says, okay, for all accounts that end in 004, they all share a single lock. But that at least allows multiple different accounts to make forward progress in the same bank without making it, so onerous that you have to have a different lock for every single account. All right? Okay. So now we're back to our shared buffer example, and now we're going to actually take a look at a situation where we have multiple producers, right? So we said that our previous solution worked as long as we had a single producer and a single consumer. Now let's see what happens if we have 2 producers and a single consumer. Well, imagine that the order of execution of these 2 producers was that first producer 1 comes along and it puts its character in buff in, and then producer 2 comes along and it puts its character in buff in, and then producer 1 comes back and increments its pointer, and producer 2 comes back and increments its pointer. What's actually happening here? Remember that these pointers and the buffer are actually shared memory. So they're being shared by these 2 processes. And so in this situation, both of these processes wrote to the exact same location in the buffer. Okay, so P2 overwrote the value in P1, which is not what I wanted to have happen. Right? So I need to make sure that if I'm going to support multiple producers, that I basically treat the sequence of 2 instructions as a critical region, right? It's a region that I have to make sure that I do both of these things before another process can go ahead and start execution of that same piece of code. And so going back to our piece of code that we had, so we've already added the character semaphore to make sure that we do a send before receive. We've already added the spaces semaphore to make sure that we don't overflow our buffer. And now we're going to add a mutual exclusion semaphore around this critical region. Okay, and so it's going to make sure that a single producer is going to grab this lock and be able to put something into the buffer at location in. And similarly, a single consumer would be able to grab the buffer at location out and be able to take a character out of the buffer. Okay, so we see that semaphores are really very powerful. We're able to express lots of different things with them, right? We've expressed precedence constraints, which are these two arrows here showing that the send had to happen before receive, and that the producer couldn't put too many things into the buffer. And we also have our mutual exclusion relationships, where we had to make sure that when we're accessing things using the in and out pointers, that we're doing this whole sequence of instructions, which is defining a critical region. We do it all together. Okay? Any questions about this? All right, so now we've actually implemented a entry FIFO buffer in shared memory, which supports both multiple producers and multiple consumers. Okay, well, so now we want to ask ourselves the question of, well, how do we actually go about implementing these semaphores? Because in order to actually deal with these semaphores, you basically have to treat the control of it as a critical region, where you're going to read the value of the semaphore, modify it, and write the value of the semaphore back. That all has to happen without being interrupted. But how are you going to, have a critical region if you're trying to, define these wait and signal operations in the first place? And so the way that we actually implement these wait and signal operations is as follows. There's actually a couple approaches. The first is that we use a special instruction which does a read, modify, write, all as part of a single instruction. Okay, so because an instruction in itself cannot be interrupted, that means that you're essentially doing the critical section without having anything else interfere in the middle. Okay, and so this is the most common approach, is that ISAs add these special atomic read, modify, write instructions to support these atomic instructions that are needed. Another way of doing it is if we go back to our operating system and what we learned there, we learned that we can augment our instruction set architecture by using the operating system to call system calls. And what could the system call be? Well, when we talked about it in the past, we said suppose there was an instruction that my instruction set architecture didn't include, like multiply, and I wanted to support a multiply instruction. Well, what I could do is I could make my multiply instruction be a system call, which goes off into the operating system, and then the operating system in hardware effectively implements a multiply using other instructions. So I can do exactly the same thing in order to implement my signal and wait operations. The reason that it works is because remember that when you go into your kernel mode, or when you go into your supervisor mode, with the one with higher priority, your kernel is uninterruptible. Okay, so if I'm implementing signal and wait as part of my kernel or part of my supervisor mode, then I am guaranteed that I'm not going to be interrupted while that operation is being performed, right? So I will get to execute the entire critical region before something else can come and be executed. And so that's another way of possibly supporting handling of the signal and wait operations. And that's in fact often done in simpler operating systems. Okay, so we're almost done talking about synchronization, but there's one other, issue that we need to concern ourselves with, which is kind of shown in this example right here. So, what can go wrong even when we use semaphores? Well, suppose, once again, that I'm back to my ATM example, except that this time, instead of trying to take money out of my bank account, I'm trying to perform a transfer. Okay? And so, my first person here is going to perform a transfer from the 6031 account into the 6004 account. And my second guy is trying to, transfer $50 from the 6004 account into the 6031 account. Okay? So, what's going to happen? Well, here in the middle, I have my code, which is going to basically look at the balance of account 1, subtract that amount from it and update it, and then look at the balance of account 2 and add to it the amount that was transferred, okay? So clearly I need to do these two things as a critical section. So what I'm going to do is I'm going to go ahead and I'm going to add semaphores for making sure that I can handle these things as a critical section. So what do I have to do? Well, in this case, I'm dealing with 2 bank accounts. So I have to actually grab 2 locks. So I'll wait for the lock for account 1, then I'll wait for the lock for account 2, then I'll do this critical section, and then I'll signal them so that the next person can do the same thing. Does anybody see any problem with this? I'll show you what the problem is. The problem is the following. Suppose that the order of execution here was that thread 1 comes along and it says, wait for account 1, which is for it the 6031 account, and it grabs the 6031 lock. Okay? Then in thread 2, I say wait for its first account, which is the 6004 account, and it grabs the 6004 account. Okay? Now thread 1 and thread 2 want to grab the other lock that they need in order to execute their critical region. Well, thread 1 wants to grab 6004, but it can't because thread 2 has it. Thread 2 wants to grab 6031, but it can't because thread 1 has it. So what happens? They're just stuck. Okay? Neither one of them can make any forward progress. So we call this situation deadlock. Okay? And we want to seriously do what we can in order to avoid it. All right? And so basically, we want to think about, what can we do in order to ensure that either deadlock doesn't happen or that if it does, that we can somehow get out of it. So I'll show you one more very well-known example of deadlock, and this is called the dining philosophers. And the way that this describes the situation is, imagine that you have 5 philosophers sitting around a table, and each one of them has a single chopstick sitting in front of them. And they all follow these, very careful rules about what they need to do before they get to eat. And the rules are as follows. They're first going to take or wait for their left stick. Then, if they got the left stick, they're going to take or wait for the right stick. And then once they have both of them, they can go ahead and eat until they're done. And then they put both of the chopsticks down. Okay? Can anybody see what might go wrong in this example, in this algorithm? Well, suppose they all want to eat. What are they going to do? Each one of them is going to grab their left chopstick and Now they're trying to grab the right chopstick, but they can't because somebody else has it, right? So what's going to happen? None of them are going to get to eat. Okay, so let's take a look at basically what happened in this example that made us arrive in this deadlock. And so there's a few things. So the first thing is mutual exclusion, right? We had a situation where only one thread could hold a resource at any point in time. Okay, so only one of the philosophers could hold the chopstick. Second situation is that we had a hold and wait situation where once you get a chopstick, you don't let go of it. Okay, so even if you can't get to eat, you are still holding this resource which might be valuable to somebody else. Third thing is that there's no preemption. And so once, again, it's the same idea that once somebody has something, you can't take it away from it. And finally, you also have basically this circular wait situation. So you want to think about, what could I do in order to try to either avoid or detect this situation? And one very simple algorithm which would solve the problem in this particular example is instead of just always grabbing the left chopstick, you assign a unique identifier to each of the chopsticks, and you will slightly modify the algorithm so that you always take the low stick, then the high stick, then you eat, and then you replace both sticks. By making this simple change to our algorithm, we're basically guaranteeing that there's no longer a possibility of deadlock, because whichever philosopher happens to have gotten the 5 chopstick is definitely not waiting for anything else because it also got its lower value first. Okay, so we can apply the same mechanism to our bank account, where instead of always trying to get the lock for our first account, we just get the lock for the minimum of the 2 accounts. Okay, and so what this does is that when we're waiting for lock A and lock B, even if you have 2 separate threads trying to make transfers between these 2 accounts, both of them are going to wait for the 6004 lock first. And so only one of them will be able to actually get that 6004 lock. But now the 6031 lock was not grabbed by anybody, and so you'll be able to have the one that grabbed the 6004 lock also get the 6031 lock. Okay? And so by doing that, you avoid deadlock. Any questions? All right, great. So you'll get to do a bunch of these examples in recitation tomorrow, and we will see you on Thursday. Thank you.